Let's go over Dijkstra's algorithm over this example from assignment 11. Let's first go over the algorithm. The algorithm is really simple. The 3 step and then we repeat. So we first set all the distance to be infinity except the 0 with 0, obviously. And the algorithm is characterized by a series of visit. Okay, a visit. When visit each node one by one. Okay, and basically if there's 9 nodes this time, you just visit 9 times. If you want to make a computer program, and I guess you have just one recursive function called a visit and give it nodes. And once you visit, and then that function will carry out updates, visit neighbors. So don't confuse the visit and updates. So now 3 steps and repeat. Each time you pick one node to visit. So first step, so all infinity distances and 0. First step, select unvisited nodes with the smallest distance, tentative distance, smallest, not necessarily the neighbors, okay, smallest globally, and then to visit. And then from there, update the tentative distance of all its neighbors. The nodes itself is not uploaded. And then visit there and mark it visited. And you're done. So then you select next one, unvisited, because updated and some of the distance may change from infinity to some reasonable numbers. And among those numbers, you pick a smaller one. Once again, not necessarily the neighbors of the visited. And then to visit next time. When you visit, what do? You update neighbors. And update neighbors, and then choose the smallest to visit. So, and let me walk through a couple of steps, and then you will know. Okay. Now, so everything is infinity. So whenever I visit, I will circle it. So first, of course, visit the 0, and I will put 0 here. That's the visit 0. And now the first step is done. I choose smallest. Now update its neighbors. So this one has 4, and the slash from 0. And then the 2 neighbors. 7, obviously it has distance of 8 from 0. So the action of the visit 1 is done. Now 3 steps. So now then to record this result, I can put in this table around up here. Look, and visit 1, the updated, I will put the green, update this one, 4 and 0. So now in this table, it's 1 still as red, that's the visited, and the rest is 0. Note, okay, I see many mistakes. They put this 1 as well. Never put this 1. Okay, and this is not 1. It's updated doesn't mean you visit. Each time you only visit 1, and that act as a result of that visiting, and you update its neighbors. Then you're done. So the updated I put in green in this here. So this is updated, this is updated, but this is not visited. But you're visiting one, and what do you do in there? You update its neighbors, and then you're done. Now, then go back to here. You select again unvisited. Yeah, select unvisited. And with the smallest tentative distance, remember the rest is still infinity. Only 2 has numbers. 1 is 4, 1 is 8. At this time, the second time choice, obviously, is 1. So now this second node is node 1. So I put 1. As a result of that visit, then you will, so then I will put a sequence 1, So I put sequence. You have a 9 visit, you have a chain. Okay, the result is the chain. So you have 9 visit. So now I have 1. So that's the second one. If I circle all of them, well, I'm done. So each time, so now 1. So there are 2 neighbors. So this one, number 2, you get 12. Are you visiting number 2? No, you're not visiting number 2. Okay, from 1. You're updating number 2's distance from 1. Okay, you're still visiting. And also, you're updating number 7. So 7, you will have this. It's still 8, right? It's non-changed. Okay, and 7, so this is 12, 7, this 2. This should be in blue. I will put addressed but unchanged. So this 54 plus 11. Okay, it's not, it will be 12, but it's not picking, so it stays. But it stays doesn't mean we didn't address. We still did work. We are visiting number 1 and updating 2 and 7. With 2, change it to 12, and 7 stays 8. But we did consider this link, but we discard this link. We don't use this one. Okay, so we're done. Updated. So now we pick. So we have 3 numbers. We have number 12, 4, and 8. So now, is this a semantic mistake? Okay, some people think, well, I just search for the path. I continually going this way. No, you don't go in that way because you pick the minimum. So in this case, which one is smaller? Okay, unvisited, all of them are visited. And then, of course, a smaller number is number 8, not number 7, number 7. So many have a mistake from here. You will choose this instead of 2. Okay, so now number 7. So it's number 7. You put here red. You can read. And then now whenever you put this table, okay, so number 7 you're choosing, and then you're updating. They have 2 neighbors, 8 and 6. So 8, 6, you will get 9. So 9 from 7, right? So that's this one. I put in green. And then you will have, so now here, 8, 15. So 15 from 7. So 15 from 7, put in the table. So if you put the table nicely, and then you will put like this. And then you put a 1. Once again, when you visit, you update neighbors. There are 2 concepts, visit and update. Okay, the action of the visiting is to update neighbors. Once you update the neighbor, this visit is completed. You mark the visited. So now visiting number 7. We're done. Now, what's next? And of course, you do the predecessors. That's from 2. That's pretty easy. You put a predecessor like here, 9 through 7/7 predecessors, and 8/0 from this, and so on. And so now once you're done, so then 1, then we put over here 7. I put the chain of the visit or the sequence of visit. In fact, in the homework, I just want you put the sequence of visit, and you may not have time to complete the table, the chart, like in the homework. And then as long as you show this visit, you work this way on the paper by hand. So now, and sometimes you may have to, then you keep going. So what's next? Next would be number 6. Okay, number 6. So then why you number 6? So this is 9. This is 12. Then you look at the table, 9, 12, and 4. So smallest one is number 12. So then number 6. Okay, smallest one. Smallest distance unvisited, not necessarily the neighbors, but in this case, it is in the neighbor. So that's that. So 6. So now when you may have to update the neighbors, because if it's neighbor, if as long as it's unvisited, and then you may need to update it and see if you need to change it. Like in this case 7, this case, okay, it's this neighbor is already got 8, but you still consider this 11, you removed it. So that's very consistent every time you visit one. And if you want this format in the table, each visit you have one table and only change one of this key to 1. So red, look at my color code. So I think you know how to do this now. Important is most type of mistakes, you sort of like search the past, whichever way you can go through. No, that's not the way. You look for the smallest, even if it's not its neighbor of the visited, smallest one with the distance, tentative distance, and you choose that one to visit. By visiting, I mean go there, visit, and update its neighbors, and so on. It's repeating, very small, a simple idea. So I think by now you probably can even write a computer program. I suggest that the routine is recursive, and you just call it visit and give it, choose smallest, mark it visit. And actually 9 steps. If you have 9 nodes, just 9 steps, the whole thing will be done. Okay, the result is actually the sequence. Apparently, I skipped some steps. Again, you see this whole thing completed. 1, 0, and 7, 6, 5, and keep going. Every time you update the distance, Remember what we did with the 7, and you're supposed to update, but you don't update. But then sometimes cases you get the number, and next time you have to update it. But just follow this algorithm. Eventually, all this table will fill up, and then when all visited, you will on this side you will have basically 9 of this, 9 of these tables, and each one visits. So 9 of this. Each time you only visit one. I put this. Okay, for example, in this visit, node number 3, almost toward the end, no change, but you still visit. But the result is that okay, all these are addressed, because number 3 is neighbor, so this. But it's whenever I say blue, it stays the same number, so addressed. And but it visits that one, and finally visited 4. You have 9 nodes, you visit 9 times. When now everything is visited, you're done. So it's very strict, rigorous algorithm. Okay, and then in the end, so this node number 4 is the final, but then visit that one. Well, nothing update, but nothing update, you still explore, see if you need update. As a result, there's no update. But in any random graph or something, you may still need update, okay, even to the last step. So that's once you're done, so this is entire answer. Okay, it's very easy from here to extract the shortest path tree. So what do? So you just go backwards. For example, 0, it's then goes to 7. So you will say from 4, you will say, okay, predecessor is 5, right? So 5, and then from 5, predecessor is 6, and this, and you construct a tree. This table can easily construct a tree. And of course, if you work this way in a test or in a homework exam, but if you write nicely, you can extract this from this, but a little bit messy. But in test, it will take a lot of time to write all these tables. And probably that's the reason I make this video. I don't want to use too much time to type up the table, but you just work this way. Actually, I can work this way, and in fact, I do this and put this in the table. Okay, and you complete this search and you write down as 21/5. That's this path. And whenever you need update, just cross it out and change. So on a scrap paper, and then in the end, all I want you to show, you may or may not need to show this, but I want you to show the sequence of the search. So in this case, in homework answers and visiting paths, for example, the sequence is 1, and Remember, the visiting path is not the shortest path tree. Okay, don't confuse this. The visiting path is the sequence you actually visit, follow the algorithm, okay, by choosing the tentative minimum distance, the nodes that has minimum distance, okay, not necessarily the neighbors, okay, not trying to tunnel through or things, not like that. The criteria for choose next to visit is important part, is very the key idea of the Dijkstra's algorithm. So once you write this sequence correctly, I know you actually carry out the correct search. And then you write the shortest path tree. You can also, from this information, a little bit challenge, you can do. So that's what I did. So this is shortest path tree, 07654. You can just look for these numbers. So 4 with 21, you're from 5, and 5, 11, you're from 6, and 6, and then from 7, and 7 from 0, and so on. Then you write this branch and this branch, shortest path tree. And I hope you got it. You can create some of your create the graph. Actually, this graph I created myself, and just try to play with it, and then you'll have every problem you can solve it perfectly. All right. Hope this is helpful. Good luck. Now let's go over this problem, Dijkstra's algorithm for directed graph. And let's figure out the two steps. You visit and then update the neighbor distance. Remember the global, and then choose next visit. The next visit is the lowest distance to the source, not necessarily the neighbors. So two steps. Visit, okay, and then update. And then choose next, and then visit. How you choose? The smallest distance, okay? Not necessarily neighbors, but when you update neighbors, okay, and smallest distance. Remember, not necessarily neighbors. Okay, by visit, I will do a circle. So now let's begin. Okay, when I visit, I will choose a circle. So first, obviously, I visit this first one. All right, and then update neighbors. So this one and number 4, the distance obviously is 3/1. Just pay attention to my notation. Is distance of 4 is 3 and goes through 1. Number 5 is distance of 10, go through 1. So update. Now choose the closest smallest distance to visit. Now a circle. So now I'm drawing here the sequence of visit. Sequence of visit. Visit to 1. Now which one is small? 10 and 3. So obviously 10 and 4, visit 4. Now then update the neighbors. So then here from this one is a directed graph, so it cannot go to the 5 and then goes through 6. So 3 plus 6, you will get 9, and through 4. So update. Now you update it and then choose. What do you do? So you have a 10, you have a 9, and what do you do? Obviously it's 9. Okay, and then visit and then update. Have 3 neighbors in this case. So you have number 3, 9 plus 5, you get 14 through 2, and 6 and 7, you have 15, 6 plus 9 through 2, and then you all the way to 8, 9 plus 12, 21 through 2. So there's 3 neighbors. That's called update. Okay, you update is not visit. Update neighbors and choose next visit. Now I have updated. Now I choose smallest. Okay, so I have 4. I have a 10, 14, 15, and 20. So this choose number 4. This is the part you have to really apply. So this one is the next one chosen. So then 4, and then 2, and then next time you choose 5 to visit. This is visit sequence. All right, you choose 5. Now it only have 1 neighbor. You can actually 2 neighbors. All right, so then you have 10 plus 2. This one you get 10 plus 2. You get 12. Okay, 12 through 5. This is 12 through 5, but it will not update 4, but it's still not beat 3, so this is not using. But you explore this anyway. Okay, and then 10 plus 6, you get 16 through 5 for 3. But again, it will not beat 14 over 2. Right? So then you discard it. But you explore anyway. So then 5 is visited. Now you choose next visit. We have 14, 15, 21. So what do? You choose 3 to visit. So you choose 3 because 14 is the lowest. Now update. Remember, visit, update, choose to visit, and then visit, update neighbors, and choose. Alternate until the whole everyone is visited. You only visit one at a time and update the visited all its neighbors. Right, so now we are visiting 3. So then here is 14 plus 7 is 21 through 3. Let's compare 21 to 15. Obviously it's discarded, so that one is not chosen, so this one. And then update 14 plus 2, you get 18. So it by default is supposed to be infinity, so this 18 for now from 3. Okay, and then it has 2 neighbors from 3. So 15 stay, and then 18, so update. Update. Now what's next? You have 3 numbers. 15, 21, 18. So which one? 15 is the smallest. Therefore, visit number 7. So this sequence is 7. So this is 7. All right. So you must get the number 7. So then update. So then 15 plus 5, you get 20 from 7. So this is not chosen because 20 would not beat 18. Chosen. And then 15 plus 7 is 22 from 7. So 22 would not be 21, so 21 stays. So that's gone. But you explore this anyway. So number 7 explored. Now what's left? Unvisited. You have 3 unvisited, and you have 18, 21, and infinity. So 18 is chosen. So no, number 6 is chosen. Next, so it's this one because it's 18. So now visit number 6. Update. So then 18 plus 5, 23 for number 9 through 6. Agree? And then you will have update number 8. 18 plus 2, you get 20. 20 over 6. What do you have? So 20 and 21. Also 20 wings because it's small. So that is gone. So then, so 21. 20. So now 20. Now I have 20 and 23. Now you visit this one. Number 8. Because that's 23. So now its neighbor, it has only one neighbor reachable. So it's 20 plus 2, you have 22 through 8. So 22 and 23 on number 9, so 23 is out. So that's the final answer. So that's updated, number 8. So the last one to visit, there's only one is then number 9. So once you have this chain, so this is called a visit sequence. Visit sequence. All right, so the shortest paths form a tree. Remember, the visit sequence is not the tree. So now we draw the shortest path tree from the root to reach the shortest path. So now let me use blue. But this data is used to, you can form this data to make a shortest path tree, obviously using this data. Now, okay, let's draw it here. So obviously 1 is the root. You go from 10, 5, so then this one is using this data, so you have that one, therefore you have 3, agree, and then you have this one, 5, okay, and then next one, number 2 is from 4, oh no, not 3, 4, that's 4, let me erase this one, so number 4, yeah, just look at this predecessor information, and number 2 is from 4, okay, number 3 is from 2, okay, and then and number 7 is also from 2, 7 from 2. Number 6 is from 3. Okay, just excuse me because I out of space. So 7 is from 3. So here, no, 7 is from 2. Sorry, 7 is from 2, and 6 is from 3. That's the tree, and 8 is from 6, and 9 is from 8. Okay, my tree is sort of bended, so it's a tree structure. So then that's the tree structure. Okay, so this is shortest path tree. Now you learn the distance. So now you see the distance. Let me label the distance. So then you will have 5, you will have 10, 3, 2, you have 9, and then 7, you will have 15, 3, you have 14, 6, 18, 8, 20, and 9 you have 22. So all counted for. So now you put the distance between them, and you see they all fit. Okay, and then you from this is 10, so you add up. So then you have 3, 4 to 2, you have 6. Okay, 2 to 9, 2 to 7, you have 6, and 2 to 3, you have 5, 3, 6, 3, 6, 4, and 6, 8, you have 2, and 2, 8 to 9, you have 2. So they all fit. For example, 1 plus 10, and then the red from the distance 3 plus 6, you get a 9, and so on. So now you check. So from 1 to 10, and then 3 plus 3, 3 plus 6, you get a 9, 9 plus 6, you get 15, 6, 9 plus 4, 5, you get 14, 14 plus 4, you get 18, 18 plus 2, 20, and 20, 22. So shortest path tree. So don't confuse the shortest path tree. This is a final result with all the shortest paths and the distances labeled, and then with the actual carrying out the algorithm, you have the shortest, the visited sequence. This is sequence you visit, and this is one way. You can work on this in the tables, like in our textbook, and that is the same way. But I think I prefer this way. And you can amuse yourself, or you can just create your own shortest path problem diagrams and see if you can figure it out. And remember, okay, this is a 3-step. Visit, and then update. You update the neighbor distance with that's the lower distance, examine the links, and then choose smallest distance to visit next. Okay, and then smallest, not necessarily the neighbors, okay, globally. Okay, remember, initially you set all the distance to infinity. Obviously, the first few are naturally be neighbors. Okay, but then later on, and then the next visit, next candidate to visit may or may not be the nearest neighbor. But you follow the rule. Choose over the smallest distance to visit, and then you go in these cycles until all these are visited, and then you're done. Okay, hope you enjoy this.